Okay, so as I was saying, when we do this in the classroom, we set ourselves up as a neural network, and each of us becomes one node in that neural network, and we assign other people that we're each paying attention to. So if you imagine we're sitting in a classroom, we might have 5 people in the front row, and they're looking at the data, so something out in the world. And typically what we do is like a 3x3 grid of 9 pixels. And we're going to be trying to identify when there's a plus sign or when there's an X or something like that. So like 5 people in the front row would be paying attention to some of the pixels. And then in the second row, each person would be paying attention to some subset of the people in the front row. So if you were the first person in the second row, you might pay attention to the first, the third, and the 5th person in the front row. Or maybe you're paying attention to persons 1, 2, and 3, or 3, 4, and 5, or maybe all 5. And then if we had a third row, each person in the third row would be paying attention to some people in the second row. And what I mean by paying attention to is you're like a neuron, and your dendrites are out there, and you're connected to those people in the row in front of you. And if the neuron in front of you goes off, right, that sends a signal down your dendrite. And what your nucleus is going to do is collect all the signals that are coming in. And if it's enough to pass your threshold, right, then your activation function will go off and you will send a signal out to the people behind you. So that's what we normally do in the classroom. And we then create a learning environment for that by each time we show a stimulus to the front of the room, we ask the back of the room what the network saw or didn't see. And then we say, well, that was right or that was wrong. And if it's right, then what everybody does is strengthen the connection to anyone who gave them, in a sense, the right answer. So if I'm in the third row and I'm paying attention to 3 neurons in front of me, and those 3 neurons sent the correct signal, then I would increase the weighting of those. And if they sent me the wrong signal, then I would decrease it. So after a while, what we find is our weightings are starting to change. And if all is well, the network starts to perform better. We do a better job at recognizing whatever we're trying to recognize. So we can't do that when we're distributed, at least not in a way that is as much fun. So we're going to use some actual software, and we'll play with that today. Okay, so let me get to the page that's going to let me go to the next one. So here's a picture of the classroom, what we would do. So let's imagine we've got these folks in the classroom, and here's the stimulus that I was talking about. And these are the people in the first row, and each of them is paying attention to one of these 3 pixels. And then the people in the second row, Ari is paying attention to Din and Eli, or Eli. Bree is paying attention to Eli and Cal, and Fra is paying attention to Cal and Din. If you're wondering what these names are, they're just alphabetical order and things that only have 3 letters, so it fits in the damn box. Finally, in the back row is Gil, and Gil pays attention to Ari and Bree and Fra. And then the way that would work, this is sort of a storyboard. So here's the stimulus. And so Eli raises her hand, Din does not, and Cal raises their hand. And the reason they did that is because Cal sees a black pixel, and Eli sees a black pixel. Din sees a green pixel. So we're firing, in this case, if we see a black pixel. Now we go, what does Ari see? So Ari sees Eli raising their hand and Din not raising their hand. So now we're over at number 2 here. So here's Ari looking. And Ari says, well, that's a little bit of signal, but it's not enough for me to raise my hand. And then Bree looks at Eli and Cal, and Bree says, whoa, everybody I'm looking at has raised their hand, so I'm going to raise my hand. And then finally, Fra over here looks at Din and Cal. Cal has raised their hand, but Din has not. So Fra says, no, I'm not going to raise my hand. And then Gil is looking at Ari and Bree and Fra and says, well, I see only one of the 3 raising hands, so I'm not going to raise my hand. So in this case, this network is basically saying, no, I did not see the pattern I was looking for. Any questions? Nothing?
So is it kind of like a yes, no? Like I know there's like a threshold, but
yeah, so in this case, the thresholds are, we didn't address that here. And so we're just treating it as if everybody, or if the majority of the people I'm paying attention to raise their hands, then I raise my hand. But the raising of the hand is a yes or no binary output. So it's that step function, right? So if Eli sees it, then Eli raises their hand. And Bree is only going to raise their hand if everybody they're looking at raises their hand. So they're looking at Cal and they're looking at Eli, and so they raise their hand.
And so is it like conceptually like similar to a circuit kind of like thing, or?
Yes, it's a circuit that has this kind of weird quality of taking its inputs and combining them mathematically in a summing fashion, but it's a weighted sum is what we're going to eventually get to. So we aren't dealing with the weightings at this point. We're just dealing with the connections here. But what we'll add next is how to think about the weightings. So now we might sort of say, what if the input were a different pattern? So what if the input were black, black on the bottom, and then green on the top? So if I look over here, if it's black, black on the bottom, right, then Din and Cal raise their hand. And then Fra raises their hand, because Fra is the one who looks at those 2. If all 3 of them are black, then Eli raises their hand, Din raises their hand, Cal raises their hand, and then Ari raises her hand, Bree raises their hand, Fra raises their hand, and Gil raises their hand. And so all of a sudden it's like, yes, we see the pattern. Now, I just want to show another way that we could look at this. So instead of drawing the diagram where we have the nodes connected by lines like this, right, what we can do is think of it as a spreadsheet. And so here I have Ellie, Din, and Cal, and Ari, Bree, and Fa, and then Gil at the back. So Gil is looking at 3 things. And so I'm going to imagine that I put a weighting on each one of 0.33, or it's actually 0.333333. And Gil's threshold is going to be 1. So if every input is a 1, then Gil will reach the threshold and activate. Fra is looking only at the second and third ones in the row before him. It's only looking at Din and Cal. Bree is looking at Eli and Cal, and Ari is looking at Eli and Din. Eli is just looking at the first input pixel. Oops, and these should be 1 and 1 here. So it's a typo right here and a typo right here. So Din is only looking at pixel number 2 over here, and Cal is only looking at pixel number 3. So I'm going to jump to that spreadsheet itself. Let me make sure this works. Are we still here? I just got to disconnect signal. Yes, okay, great. So I'm going to switch. Okay, are you seeing this Google Sheet now? Okay. So here's where the errors were. So I'm going to fix these guys right here. So we see now that Cal is paying attention to, and over here we sort of see what they are looking at. So Din just looks at the middle pixel and so on. So right now, the network is saying no, I don't see the pattern because Gil does not fire. Now, suppose we went through and said, but Gil was supposed to fire. We wanted to see the pattern that we're looking at over here. We wanted that to be the thing that we're trying to recognize. And so what we're going to do is we're going to kind of go back through the network and say, so of the people that Gil is looking at, did anyone actually activate? And if so, then we should bump them up. But we look and say, no, none of them activated. So Gil is looking at Fra, Bree, and Ari, and they're all turned off. Okay? And we say, okay, now let's look at Ari. And who was Ari paying attention to? Ari was paying attention to Eli and Din, but neither of them fired, so we don't want to do anything there. And the same is true for Neuron, for Bree, and for Fra. Then we go back here and we say, let's look at Eli. So Eli was paying attention to this first one here, and there was a 0 coming in there, so we don't do anything with that. Din paying attention to just this middle one, and that one was actually a 1. So what I'm going to do is I'm going to increase that weight by a 0.1. So I'm just going to supplement it a little bit. And then I look down here, and Cal was looking at this last pixel, and that was on, and Cal weighted that with a 1. So I'm going to strengthen that and give it a 0.1 now. And so what I've just done is adjusted the weights in the network. And now if imagine we do that again, I'm going to now look at Gil and say, so Gil still said no over here with his activation, but this 0.33 here was with a yes coming in from Fra. And so I'm going to strengthen that one because Gil's sort of saying, I got it wrong, but Fra sent me the right information. So I'm going to change that by 0.1. So I'm going to move it up to 0.43. Then I go back and I look at Fra. I say, so Fra, you got it right. So who sent you a 1? Because we want to strengthen that connection. And so I'm going to change these to 0.6. And then I look at Bree. Bree got it wrong, but it did have a 1 coming in here, so we're going to strengthen that one to be 0.6. And similarly with Airy got it wrong, but it should have paid more attention to DIN here, so I'm going to change that to 0.6, and so on. So what we did there was we started at the back of the network, and we went back through the network, and we said, let's give extra weight to anybody who gave us the right information. So are the weights related to probability? In the long run, you can think of them as related to probability, but within the model itself, it's better to think of them as they're just coefficients, in the same way that your grades are going to be made up of 30% for the midterm and 40% for the final and 10% for class participation. So you want to sort of think of those as are they necessarily 1 or less than 1? Not necessarily. Sometimes you keep them in the range from -1 to +1, but that's an arbitrary way. That's something that you build into the model the way you're designing it, and there'll be advantages and disadvantages to doing that. Sometimes you want weightings that can go far higher than 1 because some input is extremely important compared to other inputs. Now there's an interpretation of these which is related to the way linear regression works if you've taken statistics. If I do some research to try to figure out what predicts how much somebody earns when they're 30 years old, and I have variables such as how many years of schooling they had, how many years of schooling their father had, how many years of schooling their mother had. I might have what we call a dummy variable for their gender identity, for their race, for their nationality, for their immigration status, and so on. And so I do a lot of research, and I find out that the thing that most affects how much people make is how many years of education they have. And eventually what an economist or a sociologist would come up with is an equation, and it would say some number times the number of years of education is going to contribute to the amount that you're earning when you're 30 years old. And then some coefficient times the variable of what your gender identity is or what your nationality is. That there's going to be a contribution being made by these different variables. And so you can think of the weights as when Gil tries to decide whether or not to fire, there's a certain contribution of information coming through the network from Fra, and a certain contribution from Bree, and a certain contribution from Airy. Are they representing confounding variables? Say more what you mean by that.
I'm not sure if I'm remembering this right, but you know when you do a linear regression and you're trying to see like X impacts Y by some amount, and you have like ABC may also impact Y. Like, is that how you can kind of think about it? Like,
yes.
You have all these different inputs. Okay.
So when it's a multiple regression, when you've got all these different inputs, and you're saying, look, we have to look at all these things because we don't have a theory about how this works right now, and so we're gonna just sort of throw everything in the pot, stir it around mathematically, do some computations with lots of data, and then we're going to say, we have found an equation which very nicely predicts the outcome we're interested in, and here's the contribution from each of those variables. So yes, if you've seen multiple regression with lots of variables in it. This is essentially the same process. Okay, I'm going to jump back to the other window now. Let's see if I here, there. Okay, so we want to do a quick little aside here, and this is not this is sort of not critical to understanding the gist of how a neural network works, but it will, the visualization of this will make things a little bit easier to understand, I think. So let's imagine that the world that we're looking at is this 6x6 grid at the top here. And imagine that what we're looking for is the letter T. So the dark pixels here, you can think of them as having the value 1, and everything else has the value 0. So what we want to do is we want to have our network recognize the letter T, but that letter T could be written in a lot of different ways. It could be very small right up top here, 1, 2, 3, 1, 2, 3, like right there. I'm assuming you can see my arrow. Is that correct? My cursor? Okay, great. So you could also have a T down here, or you could have a T that goes all the way across and down here, and so on. So what we want to do is we want to train a network to recognize letter T. The way that we're going to think of that is take this 6x6 grid and spread it out into a line, as we see with the blue thing here. And then we're going to have neurons, which are the big blue circles, and the neurons are connected to various of these input pixels. And then there's another row of neurons behind that, and that second row of neurons is connected to some set of the first row of neurons. So when you take a network like this, if you have more than one layer, as we have here, that's why you call it a deep neural network. So a deep neural network is one that has lots of layers. So the next quiz question here just says, if we have this pattern of a T, what's the actual data look like? And then in the blue, we have the solution to that. So this data, this T, would look like this array of ones and zeros. So we've got 1, 2, 3, 4, 5, 6 zeros representing the top row. And then we have 5 ones because of the top of the T. And then there's a 0 at the end of that. And then there's 2 more zeros for this white space here, and then a 1, and so on. So again, this is not necessary for understanding, but it's some of the visualizations you'll see, you might sort of ask yourself, how can that visualization of a line of pixels be a scene or be a two-dimensional image? So what we do now is we have another Google Sheet that does, we're just expanding it now. So now I have a 3x3 grid, and the blue are the number 1, and the beige are zeros. And then we look and say, okay, so neuron 1, let's say it's connected and it's just looking at cells primarily at the first 3 here, over here. So it's got a high weight on number 1, number 4, and number 7. And it's got very low weights for everything else. One of the things that you'll see sometimes is you'll see a picture of a network drawn where some neurons are connected to just a few of the neurons in front of them and not at all to others. Other times you'll see that same network drawn where every node in a layer is connected to every node in the layer before it. But some of those connections might have weight 0, which is equivalent to not being connected. So, so the way that neuron 1 has a 0 weight for number 3, that means it's not paying attention to this pixel here at all. Okay, so now what we're going to do is we're going to say, let's think of a different problem for a moment. So now I have a 5x5 grid, and what I want to think about is there a path from the top row to the bottom row? So you can almost think of this as there's certain kinds of games like Connect 4 and things like that that have this kind of question in them. So we're going to, if this connection right here, we would say that's not connected, because it has to be the case that I can start here and go straight down, straight across, down, across. So I'm down, I'm at the bottom. Everybody see what I mean by there is a path and there is not a path? So now what I'm going to do is I've got a little program running behind the scenes here, and it's a 1-layer network. We've got 1 layer of 5 nodes sitting here. Each of those nodes is going to pay attention to some subset of these 25. So if I hover over this, so these are the ones that that's paying attention to. Those are the ones that pays attention to. That pays attention to those, and those. And these are the weights, but I'm gonna now randomize the weights, and then I'm gonna pick a pattern, and I can ask, is there a path? So just for your eyeball, everybody should decide, is there a path or not? So the answer is there is no path. I can randomize again and ask, is there a path? No. Randomizing again. Then I ask, is there a path? There's no path. Randomize again. There's obviously no path. No path. No path. Now I ask, is there a path? And it says there is a path. So this button up at the top is not an artificial intelligence. It's not machine learning. It's a straightforward algorithm. So it's coded something which does a search starting from this square and just traces out and finds out whether there's a path of moves to the left and right and down that can get yourself to the bottom row. Okay. But what we want to know is, could we train a network to just see it? In other words, where the network is not going to have an algorithm. We haven't programmed it to do that. So the way that we would do that was we create this network, which we see here. And then each of the input nodes, so input node 3 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22, 24. And so you can see the listing of the nodes that of the pixels that this node pays attention to. This is the weighting that this node has for the final decision. These are the weights that it gives to each of these input nodes. The plus and the minus is here so that I can reward or punish connections that get it right or get it wrong. And so if I were to randomize and my network said there is not a connection, but I'm going to say, actually, there is a connection. So if I click match, what I just did is I just told it that it was wrong. And then it randomized again and it said there's no, and I said, I agree, there's no match. This time it said no, but I say there is a match to the pattern. So I said yes. This time there is none, and it said no, and so on. So that's teaching this network on experiment by experiment by experiment how that works. Now I can tell it that what I would like it to do is to do 500 of those automatically. And so I'm going to just tell it to train for 500. So what it's going to do is going to generate a random pattern. It's going to run the algorithm that detects whether there's a path or not. And that algorithm is the one that I programmed in. And then it's going to ask the network, based on neurons firing, does it think that there is? And then it'll tell us what the stats are. So it takes a moment there. So it got 49.4% of them correct. And notice that some of the weights changed here. Right? Some of the weights got negative and so on. So I'm going to do I'm going to do 5,000 this time. And I'll just look at the weights and see what happens. So now my weights adjusted, and you can see the weights on this node over here, these are going off the chart, gigantic. These are as well. These are tending to stay small. Now it turns out that this particular little neural network is totally lame. It never gets much better than 50%. And 50% is what you can get by chance. So we might say, so why is this network not very good? So the answer can be a couple things. It might be that this is a problem that doesn't lend itself to solution with this kind of a network. Right? It can be that the amount that I'm correcting for each time is wrong, that I'm taking, if I change the weights each time we get something right or wrong, maybe I'm changing it by too much, or maybe I'm changing it by too little. Right? So all of those things, that's called tuning your model. So the act of trial runs like this is called training, and then the act of changing the values of how the model works is what we call tuning. So that's a great question. Now it turns out that this model sucks so badly that I'm going to do another 5,000. And then another 5,000. And another 5,000. So we get up to 20,000. And I'll say it's just barely. That comment just disappeared. So what if you keep testing? Say you had a grid that is 3 by 3. Could a model trained on that be applied to a model that's 6 by 6? Okay, so a very astute question. It depends what the model was being trained to look for. So for example, I might have a model that say is looking for any 3 by 3 grid that has most of the squares on the left illuminated and the squares on the right not illuminated, right? So it's basically looking for like a left-hand 3 by 3 grid. So that little model can kind of scan around, and it could find all the places where that pattern, that sub pattern shows up. there's a in the Machine Learning for Humans book, there's a mention of a thing called convolutions, and convolutions work a bit like that, where you have a small grid of nodes that's tuned to look for a particular part of the pattern, and it can scan over a larger grid. That may not be quite what you meant there, but I'm going to leave it at that for the moment. Okay, so all of that was really meant not to be a highly exact science in a sense, but to give a little bit of a sense of what we mean when we say training, what we mean when we're showing a value to the machine, to the network, and then we're telling the network to make a guess, and then we're revealing to the network what the actual answer was. And if the network got it right, then what we're going to do is we're going to strengthen the connections that we're passing along something that was going to make us say yes. If the network got it wrong, then we're going to weaken anything that was pushing us in the wrong direction. At the end of that process, what I'm going to have is a whole set of weights, which I'm going to leave fixed. And I'm going to say that set of weights with that pattern of inputs is actually going to do a pretty good job of mapping a set of data inputs to the correct answers. And we're going to say that that is basically getting my network to learn a function. Now, why do we say it's learning a function? So if you remember from Thursday's lecture, at one point we drew a picture and we said, you can think of a machine learning model as something which maps from a long string of ones and zeros into, in this case, just a single one or zero. So what I've got here, I've got 25 squares that can be on or off. So every single pattern that's possible in this 5x5 grid can be represented by a 25-bit number, which is just a number, right? And what we want to do is map each of those numbers, which each one represents a pattern. We want to map that to there is a path or there is not a path. So over here on the left, what is the number? It's 11101 10111 1110 01001 11000. And that should map to 1. So the function operating on that should give me a 1. This binary number, 001010011000000110010, that will map to 0 because there is no path here. The neural network is accomplishing that by putting together the correct long list of weights. So the model is just this collection of weights. And what are they? Let's say this model was very well trained, right? Then the collection of weights is just going to be 115, 124, 122, etc. So this long array of weights is the set of things which is going to accomplish that function. Is there a better way to design a network that can decide the path, like our edges touching all the way through? I'm not sure what the last question there means.
So I mean, like, I kind of see like how it's working as is in the current neural network, but is this the best way to solve it? Because I'm thinking like, what if you trained it to see like, does each square have an edge covered by another edge all the
Oh,
way to the
so
bottom? Yeah.
so definitely this is not the best way. There is a better way. There must be a better way because this way is pretty lousy. Um, and the only purpose here is to illustrate like what the skeleton of the damn thing looks like. Um, but one of the things that will come up when you're trying to do machine learning is how much of the a priori stuff like that do you put into the model, and how much do you let it um, do you give it the simplest version of the data and then let it kind of work its way out from that. The more we would do what you've said here, the less our model is going to be able to work in the wild. Does that make sense? In other words, the more that I sort of give it this a priori, when I say a priori, I mean, um, when we kind of give it some heuristics um, before we start to train it, and that's it's a smart way to do it in the sense we're trying to get it trained correctly. Um, but if it depends on the heuristics, then it might be less robust when we send it out and we want it to use other things. Um, don't brains require a lot of a priori information to work? Yes. So one of the big debates right now is whether or not you can achieve artificial general intelligence simply by having uh, more layers, more nodes, more variables, um, or do you need to build a prioris into the system? And there's a whole bunch of folks who think that uh, that you need to have a prioris, and a prioris such as causality and time and physical laws of various kinds, um, basically suggesting that the human brain has adapted itself to the physical world we live in, and so we process information already knowing that we don't have to discover the physical laws in the data itself. And yes, so we apply a priori things to novel situations, but one of the reasons that it works is because those novel situations are happening in the world of which the a priori things are true. Right? So it would be harder for us. It is harder for us, for example, to be smart in weightlessness or in the dark or when we're upside down in water. Those become much more difficult for our eyes to make sense of the world. Okay, so let's slide down here. I've lost my slide. Okay, over here. So what we want to do now is ask you to open up a. I'll put this in the browser. I mean in the chat. Oh, that's not the right teachable machine. So tell me if that opens up something reasonable. Sorry, something went wrong. Okay, let's try. How about just a part? Okay, so So this is the website for a thing that Google has out there called the Teachable Machine. Um, and let's, oh, I can't do it there. Got to do it here. Is my audio on for you? No. Okay. I'm going to unshare and then reshare here. Sorry.
People are training computers and creating machine learning models to explore all kinds of new ideas. New ways to interact.
Yes.
To understand the world. To play. And experiment. But machine learning is pretty intimidating to get into. So we've been wondering, what if it wasn't? With Teachable Machine, we set out to make it easier for anyone to create machine learning models without needing to write any machine learning code. When it first launched in 2017, it allowed everyone to get a feeling for what machine learning is all about. But now, Teachable Machine puts the power of machine learning in your hands, allowing you to save your models and use them in your own projects.
So let's say you want to build a model to recognize you versus your dog. You just open up the site, record samples of you and samples of your dog. Click train, and you instantly have your own machine learning model, which you can use in your sites, apps, and more. You can upload your model to host it online, or download it to work entirely on device.
With Teachable Machine, you can create custom models for all sorts of things. Using images, audio, or even poses. Personalized machine learning models for the things that matter to you. And folks have already been trying it out, using Teachable Machine in their own experiments, solving problems in their communities, or even just at home. Start creating and see where your ideas take you at g.co/teachablemachine.
Okay, so that's what we're going to do. And just a quick example. Hopefully this will work this time. There we are. Let me get my microphone out of the way here. Okay, so this is a model built with Teachable Machine. And what it's going to detect is whether I'm wearing my glasses or not, or whether I'm wearing sunglasses. And I have to adjust the lighting a little bit because it turns out that lighting is everything. A couple of years ago, my older son was installing a robot at the Victoria and Albert Museum in London. It was a big robot called the Baxter robot, and it was meant to be folding laundry. And he sent over the specifications for how it had to be installed and what kind of lighting it needed and so on. But of course, the folks who work in museums have a different theory of lighting because it has to be beautiful and it has to work in the exhibit and that. And so they had various spotlights on this thing and all. And it turned out that the poor robot could not handle it. It couldn't find the laundry, it couldn't do all the things it was trained to do because the lighting was wrong. So if you're worried about the singularity coming, you can kind of sleep calm tonight because it's not happening anytime soon. But let's see if we can't get this thing going. So this is using my webcam. And right now it says I've got no glasses on. So I'm going to stare at it. And you notice that when I actually look at it, but if I take my headphones off, so it's not doing a very good job there. But watch this. If I take those off and I put my sunglasses on, So now it's certain that I have no glasses on. And now it's pretty sure I'm wearing sunglasses. And it doesn't matter which sunglasses I have. I can actually get another pair of sunglasses here. And once again, it's pretty sure I've got sunglasses on. And I'll try a different pair of regular glasses and see what it thinks. And it's having trouble now. Now, part of the reason I think it's having trouble is because I'm using a different webcam than the one I used when I did the training. So that's probably part of what's going on. But watch this. If I go like this, you can see that it sort of thinks I might be wearing glasses. Or if I took 2 rolls of tape and I go like this, all of a sudden it thinks I'm wearing sunglasses. I did something like I hold a mirror up, right? So it suddenly sees sunglasses. So here's the question for you. What do you think the network is seeing? So it's definitely seeing pixels, but to Simrit's earlier question about can you have a part of the network that's looking at different smaller entities, so some part of this network seems to be recognizing circles, and in particular 2 circles, right? So when I hold up 2 circles like this, you can see that the circles actually have an effect. What if I go like this, right? If I have my glasses are off and I go like that, I can make the network start to think, you know, maybe those are glasses. I can even do this. So if I hold this up, it starts to think that those might be sunglasses. Okay, now you can use the same network. If you go to this page on our Quirkus site, this model works for you as well. So try it out with your glasses on, glasses off, and things like that. And then the rest of this page describes how one would use this in a code pen if you're doing it yourself. Here's when I've embedding this on the Quirkus page, and you can see the outputs down here. So this is with another webcam, and you say it's kind of bothering me that this is setting up this way. Now, if I go to the Teachable Machine site, and I'm now going to share that. Whoops. So here's your lab assignment: is to go to Teachable Thing, and you're going to do these 3 things. You have to gather some data, then you train the model, and then you're going to export your model. And by export it, that's how we're going to save it. And there's 3 tutorials here. These are sort of examples for how you can do something with images, do something with sound, do something with head tilt. I did a quick training earlier today to see whether it could recognize whether I was speaking English or German. I did another one where I trained it to see if it would catch me smiling or not. So if I'm going to try it out, I go to get started. And let's say I'm going to do an image project. And I'm going to call class 1 headphones on. And class 2 will be headphones off. And I'm going to say that I want to use the webcam. And I'm going to use this webcam. Okay, so this is headphones on. Let's get this out of the way. Okay. Now I'm going to train for headphones off. And then I'm going to tell it to train the model. So it's cranking through. Now so here is now my model that's trained, and it says I have headphones on, and now it knows that I have the headphones off. And if I put something on here, it says, oh, nope, those aren't headphones. But what if I put something black up here? Oh, it's kind of thinking those might be headphones. If I get my phone to my ear, looks a bit like a headphone. I could train it to say, no, my phone is not a headphone, and so on. Okay, so your assignment is to build something fun using this tool. And that's essentially our problem set for Vision. I'm going to jump out of here and see your beautiful faces, or let you see mine. Any questions?
So I guess when you use this teachable machine or the Google thing, it basically can answer like yes or no, right? Like, does this person have glasses?
Think of it more like classification. So you can have as many classes as you like. So, for instance, suppose you had a big stack of paper, and what you did is you wrote the letters of the alphabet on one letter on each piece of paper, and you wrote them in all different styles, different ways of writing letters. And then you have one class called A, and you show it a lot of A's. You have a class called B, you show it a lot of B's. Then what you're going to have built is a letter recognizer, a text recognizer. You could similarly, you could teach it to count by showing it cases where you had one dark object against a light background, where we have two, so you have class for 1, a class for 2, class for 3, and so on. So basically this kind of a model is a classification model.
It's like so is that like a certain level of abstraction, right? Like it's not gonna like it'll know all glasses versus, I guess, like style of glasses. I don't know if that's accurate, but
so this is a really kind of fun question, right? If you like I have a lot of different colored glasses, and I could try to see if I could get it to recognize glasses or no glasses, and red glasses versus black glasses. Um, and I could get my glasses, my other glasses, or I could take my my, let's say, other funky glasses here that look like this, and I could say, is it going to recognize these glasses as well? And maybe it will, maybe it won't, right? If I try these, because these are not round the way the other ones are, and so on. So you can train it on anything. Now, what's interesting about this kind of artificial intelligence is if there's something in the data, the model will learn it. And so if you're interested in things like AI fairness and algorithmic fairness and that, this is a great kind of starting point for it, because if the information is in the training set, and that information could even be something like, suppose you started training it with your normal glasses, and then you went and you got weirder and weirder and weirder glasses. Well, the ordering of that is a part of the data. And if the folks who program this are smart, what they'll have done is they'll have taken that sample data, and even though you might have put it in that order, they'll shuffle it up so that the machine doesn't learn something about the order in which you put things in. But if it doesn't shuffle them, then it will learn that pattern, and that'll be a part of its model of the universe or of the world.
So I guess, like, is the way that this is working, like, associativeness? Like, oh, in this picture, there are glasses, therefore this is, like, added to that data set, versus this picture, there's no glasses, it's added to the no glasses data set, and then it's like, you know, kind of A is associated with B, and then you find the pattern from there, or?
Not quite. So the model in something like this is many layers deep. So the cartoon image we did for the classroom was only 2 or 3 layers, and we only had 4 or 5 nodes. So the models that they're talking about here are going to be much bigger in terms of the total number in each layer, and they're going to have many more layers. And some of those layers are going to be what we call a convolutional layer. So a convolutional layer is a small grid. So imagine I have a grid, which is so it's 3 by 3 grid, and on the left-hand side I have 5, 5, 5 going down, and then I have -1, -1, and then I have -4, -4, -4. So on the left, 5 by 5 down the middle, -1, and then on the right, -4 all the way down. So if I sit that 3 by 3 grid over any part of an image, and assuming the images are black and white, that is going to send the strongest signal when there are sharp black pixels on the left-hand side of what I'm looking at. And so that becomes a bit of a detector for sharp vertical edges on the left. So these models have a lot of those convolutional layers built into them, and so some of those layers are going to be particularly sensitive, say, to high contrast. So if there are pixels next to each other that are high contrasting in the colors there are some of these little convolutions that are particularly sensitive to that. Others will be particularly sensitive to big expanses of color without change, and so on. And so those are making the model a much more, you can think of it as almost sophisticated or sensitive than the very simple ones we were drawing. But the same principle is at work.
Okay, interesting. I guess I have like a general question. I have a friend who's a computer science specialist, and he talks about neural networks. Like at some point, even the people who develop them don't know what the weights are like. Like they don't. It's not intentional, right? Like if you're training a model, the weights kind of change, as we saw in that example that we had.
Yep.
So like is that like the case usually? Like the people who even build it don't understand why one thing is weighted over another. So it really depends on the data set, or yeah.
So one of the big challenges is to try to understand. Well, first of all, the model is no good until it gets it right most of the time in its training, and then you test it against things it didn't train on, and it has to get those right. So there's kind of, you can have some standard setting and some testing like that. But the next level up is to sort of say, well, I'm not going to trust this thing just because it gets it right all the time. That's like going to a fortune teller, right? And the fortune teller seems to know everything, but you kind of don't believe it because it's a fortune teller, right? And there's no, like, fortune teller can't explain how they do it, and so we don't trust them. Whereas when you talk to the physicist can give you an explanation and theory, and you go, okay, the physicist says it's true, I believe it. So so the recidivism prediction software and other kind of criminal justice stuff, just getting it right isn't enough, because we want it to be what we call intelligible. So an intelligible machine learning model is one where you can kind of take it apart, see what it's firing on. Now, it turns out that when you train a network, for example, to recognize cats instead of dogs, you can often unpack the layers, and you can figure out, where does the network see whiskers? Where does the network see eyes that have kind of an almond shape versus a round shape, and so on. And so you can kind of identify which parts of the network are identifying which parts of cats, and which parts are just noticing that it's a four-legged animal, or which parts noticing it has fur, and so on. And so we think of that as intelligibility, if you can interpret that. So I think we're a little over time here, so we should be sure to let people go. So that our last presentations, I think they're on schedule for Tuesday and Wednesday, Tuesday afternoon and Wednesday morning. We'll take this to the next level, which is going to be to think about how you would train a robot where we're not just trying to train a passive classifying algorithm like this, but you're trying to train something that can learn how to make decisions as it goes through a series of actions. And we'll have a fun little connection between that and picking your career out, and not eating marshmallows, and the movie Groundhog Day, and a poem by Robert Frost. And we'll try to connect those all together. But your homework is teachable machine, train it to do something, try more than one. The posture one is especially awesome. You train it. It can recognize how your body is if you can point your webcam against a decent background. And the audio one as well. You can play at different kinds of music, and see if it can recognize genres. Can it tell country music from hip hop, and so on? So give it a shot. Last comments, questions? Okay, let's go out and get wet in the thunderstorm if you're in Toronto. and I'll see some of you tomorrow.